Okay, so this is about a project that I did about 4 years ago as an undergraduate student for electrical engineering. And we're talking here about Haskell and robotics, as you may have guessed from the cheesy title. So really, what is this about? Does it work? Yes. So we have a mission. We have this robot that we got as a present, and it has wheels and a camera, and we want to make it chase people because we're kind of mean. And specifically non-Haskell programmers, but that's like too complicated. So the main challenge, besides the usual challenges that we faced in robotics, is how to do it in Haskell. Now, I don't know, how many of you were in the FRP talk a couple of weeks ago? I was expecting everybody, but okay, that's great. That means I can just repeat that talk and nobody will notice. So I'm not going to do that. The thing is, I was the only person, I think, in the entire university, Ben-Gurion University in Israel, which have ever heard the word Haskell before. I don't know how I convinced my professor to do my thesis in Haskell. He didn't even know what it was. Also, when I was done, he still didn't know. So I guess I just did whatever I wanted, and he said, at one point, he said, if the robot moves, then it's cool. It's all cool. Okay, so as part of this project, I wrote like a basic FRP library with only the features I needed, not all the fancy switching and Yampa reactive, that kind of stuff. Okay, so here's our robot. It has a camera, a webcam really, a laptop, and a pair of wheels. They told me I should use this board. And there's two things we need to do here. The first is interface with the hardware. So for that, we're going to use the FFI, foreign function interface. How many of you have used the FFI before to interface with external languages? Okay, so I have a fresh audience. So we're going to use something in Haskell which allows you to talk to libraries which were not written in Haskell as C or whatever it is. In this case, it's C and C++. And we're going to use that for talking to the camera, or rather for reading the input from the camera and for controlling the wheels. And also because I had limited time on this project, I did not implement all the computer vision stuff in Haskell itself. I used an open source library, OpenCV, which has tons of features for image processing. It has edge detection, face detection, generic feature extraction, pyramids, watershed, all sorts of things that computer vision experts like, from the very simple to the really astoundingly complex. And we need to use that library. But we're in Haskell, and that library is in C++. So what do we do? Okay, as I said, like the main challenge, the first main challenge is talking to these non-Haskell libraries. And the second problem is, how do I do this thing in Haskell in a way that's really good Haskell style, and not, you know, let's just write the same program I would write in another language in Haskell. So the first part of the talk will be about the FFI. I'm going to really show like a few small examples without delving into all the details of exactly how it's done. There's great documentation, and also the book Real World Haskell has like a whole chapter about it. So if you want to learn more, those are good places to start. So specifically OpenCV is this, as I said, implemented in C++, and HOpenCV is the ingeniously titled package for Haskell, which just binds to OpenCV in a very low-level manner. It does not add a lot besides that, and it only binds the parts that I needed at the time. Now, when I was preparing this talk, I found out that somebody forked my project 2 years ago and has been working for 2 years on this package. So there may be a much better version. I'm sure they did a lot of work over there. I don't really know. They never contacted me, so You can use the better version also. I don't yet know what's in it. Okay, so here's an example function from the C API of OpenCV. So it's like a classic C API. It takes an input image as a pointer. The edges is actually an output image, and a couple of parameters, 3 parameters for controlling the process. In this case, canny is an edge detection function. What it's supposed to do is find edges, and the output should contain only the edges that were found in the input. So OpenCV comes with Python bindings. I should not say that word, but it does. And as you see, it's really exactly the same function signature. You give it an input image, an output image, and etc. And the Haskell bindings that I did in HOpenCV are really low level, so they're the same thing. This is FFI stuff. I'm telling Haskell how to call this function and where it's declared in which header in C, and then I say that this is the signature. It's a pointer to this data type CVR. It's just data CVR. It's like a naked data type. There's like no data in it. It's a pointer from this. Takes 2 of these. These are input image, output image, and the same. And the only thing that's different relative to those languages, those stateful languages, that here we're pure. So we have to explicitly say that this is in the I/O monad. So whatever we do here to finish the job, we have to run the monad and get the I/O done. Now, the thing that's really not good for Haskell here is the fact that this second parameter is an output. That does not make sense for Haskell. To have an output as an argument to a function. An argument to a function should always be an input in pure functional programming. And the reason is because OpenCV works like this. You have to allocate every image before you use it. So at the beginning of your program, you allocate the output image with the right size and format. And then every time you want to do an operation, you pass this pre-allocated output image to a function, and it writes into the data of that function. So that's one example from OpenCV and the really low-level binding of Haskell. And you can already see that this is not good. This is like really low level. It's not what we would want. Okay, and another thing we want to do, we'll get back to that later. Another thing that you want to do when you wrap an external library, non-Haskell library, is be able to parse and build data that you pass back and forth from that library. Because especially in C, besides pointers, you have all these data structures that are passed by value, or at least you would like to dereference some pointers and find out what's inside them. So this is the C. This struct CV size is just a pair of numbers, width and height. And the Haskell begins nicely. We just declare a regular Haskell type, no FFI magic here. The only thing that's kind of ugly is that we have to use cint. And we can derive whatever we want, classic Haskell style. And then we still don't know how to parse the memory from C because there's struct packing and all that stuff. So we have to do this horrible, terrible instance of storable. That's even a rhyme. Where we say what's the size of the struct, alignment, and we use all these FFI macros to tell our Haskell compiler how to parse and build also the C struct when we pass it back and forth from Haskell and to Haskell. So that wasn't so bad, but we're still left with this really, kind of naked data type that doesn't do much. And we don't normally do that in Haskell. We usually have like really fancy stuff that instances of some classes that make it really awesome. So in this case, the basic thing that we can do to make our CV size nicer is write kind of a lift function that takes an f, any pure function, and applies it on both the width and the height of CV size. And then we can really easily write a scale function which takes a factor and the CV size and just runs your times factor function on the CV size. So that's another example of improving the low-level bindings. And the next step would be to implement instances. There's a package called vector space, which is heavily used in Yampa, the other big FRP library. It's by Connell Elliott. And this package has classes like additive group, vector space, all sorts of mathematical things which are really useful for graphics in general, but also for signal processing where you have tons of vectors. So we can say that the zero vector of a CV size is a CV size of size 0, etc., etc., etc. And then when we're done, we can pass our CV size values into any function from any library that knows how to deal with vector spaces. And that's really cool because this is our C struct. And from C struct, we went to this really cool vector space with not so much work. I don't know of any language in which it's so easy to do this. I think in most other languages you would have to have CV size implement some interface and all kinds of stuff. And in this case, it's really easy because it's Haskell. Okay, so if you recall, we had this really ugly CV canny function, which took an output as a parameter. We don't want to do that in Haskell. And also, we had the problem of having to allocate and deallocate, and that's not what we would want. That's not how we would like to write our robotic program. So I don't like that title, so I'm going to change it. Okay. Now, here's an example system. Let's think about what's really going on here. Here's an example system where we have a camera. The camera goes to a face detection, which feeds this rectangle drawing function. And then we plus these two outputs, the rectangle image and the original image, and we get in the output and the video that came in with rectangles drawn around the person's face. So this is like a really simple program. It's kind of similar to what a robot needs to do. And let's see how we would implement this in pure functional code if we could do it however we wanted. So we would probably have something like detect face is a pure function from image to rectangle, draw rectangle, takes a rectangle and gives you back an image. And you have combine images, which takes input image, and gives you a combination as an output. And of course we have to do I/O because we're talking to some hardware here. So this gets the image from the camera, and this one, display image, displays it, obviously. So our program could look like this. Maybe not the best way to do it, but kind of straightforward. We have a loop, and here we're in the I/O monad. We extract the image from the camera. We have this pure functional expression, no I/O at all at this stage, where we process the input into an output, and then we display it. And we have a loop. So this is how we would like to do it. But as we said before, that's really, that can't be, because we're using OpenCV. We did not pre-allocate our output. And image, as we said, is mutable. And this is really how our function would look like if we were using OpenCV. We would have to do, even the face detection, which is inside OpenCV. We would have to use I/O for that, and that kind of stinks. So, what's a better way for us to wrap this interface? This is just an example of how the code would actually look. Totally imperative. This doesn't even have to be in Haskell. You can write it as a bash script. I don't know, Perl, whatever. There's no Haskell magic here. This is like really kind of dumbed down. So let's think again about this block diagram. How do we think of these types, the types of data that's flowing through these arrows? What's actually going on here? An image outputs, a camera outputs images, right? But these images are varying in time, which is something we did not talk about at all until now. And everything here is actually, this is like a snapshot of the system, but the data keeps changing over time. So the types that we might assign to these arrows is we would say that this is an image of t, an image of time, as a function of time. And this is a rectangle as a function of time. And that's a great way to start thinking in FRP. And then we could go and make a model of how we would think of our types. So in Yampa and some of the other frameworks, they're called signals, and also in electrical engineering, so we can call them signals. Camera is really video, or whatever it is, it's really a signal. It's a function from time to image. And detect face is a function from one signal to another signal. It's called signal function in Yampa. And draw rectangles is again a function from one signal to another signal. And this combines two signals into an output signal. And the display, what we have, the end result is really this. That's also a signal. So I think that's most of the FRP frameworks take this kind of model as the basis for their API. And when I started working on my project, I was thinking, well, that's great. That's exactly what I want. But as I went along, I thought of a few things that bothered me. Well, the first thing is, if we look at these signals, there's nothing that limits us from evaluating. This is the model of our API, right? So in this model, everything that's allowed should be allowed in our API. In the model, we can say, give me the video image for tomorrow at 2 p.m., but that's not possible because that didn't happen yet. That's the future, right? So this model is not causal. It lets you see the future. The second thing is that it's not finite, because I can check what happened thousands and thousands of years ago or infinitely long time ago, and even if the answer is nothing happened back then at least I'm still having, I can still have infinite information. And the third thing, which is like less important, but it's related to those two, is that even in a finite time slice, if I look even just at 1 second of video, in that 1 second, there's nothing in that model that limits me for having an infinite amount of information. I could have the video changing so fast. There are all these Weierstrass functions and Dirac's delta and all those functions that are not band limited. There's no way to represent them as sampled signals. So this is not a natural as in science, in the nature. This is not a natural signal. This is not something we really want. It's way too powerful, this model. That's our problem. Our model was not realistic, and it's really sad. And it's also too powerful. So what's a better way to represent our systems and the information that passes through them? Okay, so let's look at what nature does. Let's say you have a capacitor. The capacitor stores charge, and it's kind of like an integration circuit. The more charge you feed into it, the higher the charge goes. Or if you add negative charge or positive charge, the charge in the capacitor goes up and down. But it does not remember the entire history from the beginning of the universe until now to tell you how much charge there is in the capacitor. It does not need infinite information. Also, the capacitor can never tell you what's going to happen in the future. Intuitively, the way it works is every time you add a charge, it takes the current charge and does summation of the current charge plus new charge and gets you the new current charge. So it has finite memory. It has sequential time. It cannot, randomly access times in the future. And you can think of it as kind of like a fold, or better yet, a scan. If you're familiar with the Haskell function, scanl, this is really kind of like folding over time. So scanl is a Haskell function which you give in an input list, and the function of how to combine that input list with the current state and an initial state, and you get, as a result, the output states accumulated for every item in the list. So it gives you all the intermediate results of applying this on the input and the current state. So in reactive framework, and I think also in Yampa, scan is used as a building block for events. Events in those frameworks are signals that don't have a value all the time. They only have a value sometimes. It's like a discrete thing, like a mouse click is an event. So So scannel over time is really the same thing, except we don't have lists of data. We have like these, I just invented here a name, it doesn't really exist, temporal values where we scan over time, and over time we accumulate state. Every time a new instance of time happens, we accumulate the next output and output it. So this is the actual signature that's used in my library, and the reason why it's so much more complicated than this is because that's not enough information for computing interesting things. For example, if you want to compute differential, you need both the current input and the previous input. So you could store that in the state, but that's kind of ugly. So the easier way to do that is to always pass in the current input, the previous input, and the difference in time between those inputs. And then you have the previous state, and you're supposed to give in the current state. You're supposed to give out the new state, and you have the initial, which is the same as this B over here. And then we have these weird things, processor, which I did not even talk about yet. What are they? We'll just skip them for now, but really these are the way I represent this kind of like temporal A thing, but not exactly. So let's see some example usages of scannel T for differentiation. I also didn't mention that the first parameter it takes is a clock, and it uses that for determining the difference in time between inputs. It cannot really measure, like there's no such thing as absolute, what's the time since the beginning of the world? There's no such thing. There is, however, a natural concept of difference in time between one moment and the next moment, at least in a certain place. So that's okay with me to have a clock. And to implement differentiation, I have this function which takes the current and previous outputs. This is assuming there are vector spaces, which is why you have this funny minus and funny division sign here. But you can think as just a regular minus and division. And it tells the difference divided by dt, and that's kind of like an approximation for differential. And integration is really the same. We take the previous output and we add to it the area of a rectangle, or a trapeze in this case, that depends on the two current outputs. I don't know if it's really important to go into that, but it just gives an example of how this function can be used. Okay, now what's this processor thing? By the way, if anybody has questions, suggestions, tips, whatever, just raise your hand or let me know. Give a shout. Okay, so processor is what I decided is what I decided to use for representing signals, except that when I thought about it a little bit more, I can't really represent signals as functions of time, as I said before, because that's not realistic. So what you end up having is signals are just pure functions, or not even functions, they're just value. So a processor is really has nothing to do with FRP. It's just a type that makes it easier to do pure functions when you're in some monad, or let's say we're doing I/O. We need to do some side effects. So this lets you do side effects in a pure representational way. What this means is if I have a function that does side effects and I want to build a data structure out of that function, then I can just use the regular I/O monad and write like imperative style code like we saw before. And here we want to be able to ignore the fact that it's a side effect and hide it under the hood. So that's what this thing does. And the other thing that it allows you to do is define an allocation and deallocation functions for before and after this thing lives. So when the lifetime of a processor starts, an allocation function will be called, and when it's done, a release function or deallocation function will be called. So it hides also that detail inside. Here's an example of the 4 functions that are used to create a processor. We have a processing function which takes an input and internal state and then does something in I/O to get a new state. And the allocation function, number 2, takes an initial input and creates an initial internal state. And the conversion function takes the internal state and gives you an output. And the release function takes the internal state and gets rid of it. So everything we do is in M, and M might very well be I/O. So when we process a value, we do it with I/O. When we release a value, we do it in I/O. When we allocate, when we convert, everything we do in I/O. And this is how we define our processor. And then later on, we can use it and ignore and like forget about all that stuff. So CV Combinators is a library that wraps HOpenCV and hides the setup and teardown methods. Now, it uses an API called Arrows, which is a standard Haskell package that's been used by many other packages. How many of you are familiar with Arrows? Okay. So, if you're not familiar, ask the person next to you who is, and they'll tell you. No, really, but there's really good documentation and tons of good papers about it, so I won't go into it. But really what it allows you to do is build these block diagrams really easily in a very nice syntax while taking care of a lot of stuff that you would, like theoretical soundness and all sorts of things you don't need to think about. And I've also heard in that talk, which I was not present, that it allows for greater efficiency. And when I'm done, if anyone wants to tell me why that's true, I would love to hear. So here is an example program using CV Combinators, the same program we saw before. So here it's really easy to read. You don't even need to really know to program in Haskell. You see where the system feeds the detect face into a draw rectangle. This is kind of like a parallel operation. So in parallel to that, it does identity, which means whatever comes in goes out. And then it combines them. So that's really similar to the block diagram we had before, where we fed the input into face detection, and then in parallel, this is like the identity function. It doesn't do anything, and then we combine the outputs. So you see that the code is really similar to how you would draw it on a whiteboard, which was the whole point of this library. So that's great. And when you want to run this thing, you don't need to do any I/O here. When you want to run it, then you're in the I/O, and you call this run function. You give it something to feed into your system and something to sync, a sink where the output should go into, and you can just run it. It's really simple and nice. Okay, so back to our robot. The system for our robot is really similar to the system we just saw. It's actually a little bit simpler. We detect faces in the image, and then we try to estimate the position of the person that we're chasing with respect to our current position, and we do that by a very, very simplistic algorithm in which when we have the rectangle of the person like over here, and the center of the image is here, then obviously we need to turn left and drive forward to get to that person. And if the rectangle is really small, it means he's far away, or she. And if it's really big, then the person is really close to us, and maybe we should stop if we don't want to run over them. It depends on the point of this robot. So I just wanted to point out one more thing, which is in control theory, we have this idea where a system has feedback, and then we analyze how the feedback affects the system. I'm not going to go into that simply because I don't remember any of it, but it was 4 years ago, last time I dealt with any of this. But this is really our system, the controller, and there is a whole body of work, mathematical theory of how to optimize the controller to do what you want. For example, in this case, this is a really simple tracking system, a classic tracking system. The robot is trying to lock onto something. So like there's a whole world of how to make it, how to write it so that it locks on as fast as possible, or that it overshoots and then comes back and oscillates on the target. There's like a whole thing which I will not go into, which is why the actual robot was a bit more complicated from what I'm presenting here. So let's go back to the simplistic implementation. Look at some code. So we have the system takes the camera, feeds it into this face detection, and we're going to assume that estimate pause is the function that estimates the position, and it should output the wheels is really the robot itself, and this processor expects a pair of numbers which are speed and angle to which to move the robot. So if this is positive, we go forward. If it's negative, we go backwards, and this is left or right. So here, what our estimate pause thing does, it uses R, which is an arrow function that takes a pure function and lifts it into the world of arrows which we're talking about. In this case, the processor is our arrow. So this is kind of like lift M and all those functions used in monads, functors, applicatives. It's kind of the same thing. And so we're lifting this pure function, and this pure function is defined in terms of a single point in time. There's like no time variance here. And at a single point in time, what we have is, as an output from this, is a rectangle. And we're supposed to give back, as an output for the wheels, a pair of numbers, as I said. So we look at the distance. If the distance is greater than 1, then we go forward speed 10, whatever that means. And if not, we stop. If it's too close, we stop. The distance is defined as 1 over the area or size of the rectangle in which the face was detected. The angle is defined as the center of the rectangle minus the image width divided by 2, which would be, in this case, if the board is the image, then this is the image width divided by 2. And if the center of the rectangle is left of here, we get a negative number, and if it's the other way around, we get a positive number, and that's how the angle is controlled. Okay, so I made a very simple demo. That's part of the... I just need to find my mouse. It's lost somewhere. Okay. Okay, so here is the edge detection, and here is face detection. And I don't know if it works because I can't see myself at the same time as I look at it. Yeah, it worked before, and I assume my face hasn't changed so much since then. So there's an example. And the code for this demo is really dead simple, which is like way simpler than what you see in the Python examples. I'm not even mentioning C and C++, but even in the Python examples of OpenCV, I'm just trying to move this window here. Okay, so it's really similar to what we did before. I'm not going to go into it too much, but you see this is like this is the entire program. There's like a few lines at the top, and that's it. Takes the image, resizes it, this is another way of doing stuff in parallel, detects faces in parallel and detects edges in parallel, and then feeds it into a pair of windows. A window is like an output processor. So really, really, really simple. The full-blown FRP libraries, such as Yampa, have a lot more to them, which I did not cover here. But as we can see, that's not always necessary. So we can see now the final result. This video is played at 5 times normal speed. And that is because the robot is massive, and if it runs over your foot, you're gone. I mean, this thing weighs like 100 pounds. Like, I could not pick that thing up. It's really heavy. So I set the parameters of the program to be really, really conservative and not try to run into anything. Also, like there was one time where somebody who was controlling the robot had hit a wall. I don't know if it was this one, and a large chunk of the wall just fell. So I did not try to reproduce that result, especially not when it's following faces, okay? So yeah, there were a couple of incidents with this thing. Nobody got hurt. At least that's the official story. You can see all this extra hardware that's on top. There are 2 cameras, only one of them is being used. There's a GPS receiver, it's not being used. There is a router here that's not being used. The only thing that's being used is just my cheap laptop and a webcam. And I'm sure with better hardware, this thing could, go better. That's what happens. Okay, so how do I move on? Yeah. Okay. So that's it, really. Just wanted to tell you about a little project I did. And if you're interested in learning more, there's tons of resources. This is only a small list. There's much more. And if anybody has questions or ideas, yes?
Do you have any problems with Haskell's non-real-time nature interfacing with motors and stuff?
Interfacing with what?
So, like, Haskell has non-deterministic garbage collection and stuff. So sometimes
Right.
it might take like a few hundred milliseconds to garbage collect. Did you have any issues with that interfacing with robotics?
No, and I think the reason may be related to what they say about arrows. The way the program works is it runs all the allocations, the OpenCV allocations up front, and then it goes into a kind of a loop which does not create new values at all. All it does is invoke these functions over and over again. So I think that may be why, because we're not really dealing here with any data on the Haskell side. Yeah.
How many of those OpenCV actions did you try to chain together?
In my project, there weren't so many OpenCV functions, but there was a lot of pure code that I added onto it, integration and finite input response and moving averages and all kinds of control theory related stuff. So I can't really tell you, but it should be okay to use as many as you want. I don't see any reason why. I mean, there is kind of like an overhead. I'm not an expert on the FFI, but since the heavy data is not coming into Haskell, the images are staying in the memory as C objects, and they're not being converted back and forth from Haskell. You're just passing the pointers. So I don't know. I didn't have a performance problem here. The example I showed you before with the 2 windows, so you had 2 outputs. You had you had 2 windows here, right? One with the edge detection and one with the face detection. So that's one program doing that. And also in this kind of work, in robotics, usually the CPU overhead for the computer vision stuff for the face detection is so huge that anything else is like trivial. Okay, thank you everybody.